This is Fernando Fraternali, Professor of Structural Mechanics at the University of Salerno and corresponding author of the paper A Biomimetic Sliding Stretching Approach to Seismic Isolation, published at Open Access in Nonlinear Dynamics since November 2021. Today are with me Adam Endola and Narinder Singh, co-authors of this exciting study. Let me introduce you to the description of the unit cell of the Stretching Sliding Isolator SSI that has been designed, modeled and tested in the Nonlinear Dynamics paper. The unit cell is composed of 4 articulated limb members, arms and legs, branching out from a central post connected to the top plate of the device. This plate carries the vertical load transmitted by the superstructure that needs to be isolated from the foundation. A cap screwed to the top plate covers the central post. It can exhibit relative rotations with respect to the post due to a deformable cushion positioned between these parts. If rocking motions need to be prevented, the cushion can be removed, with the cap and the post forming a single element. The central post ends with a slider made of low-friction material built into a recess of its base. 4 corner posts are screwed to the bottom plate and connected to the limb members at the ends opposite the central post. Vertical hinges connect the limbs to one another and to the posts, while 4 membranes tendons connect the corner post to the central post. This model doesn't show tendons and can be moved by hand. The tendons are made of a material that can carry large stretching strains and that dissipates energy through hysteretic response. We let the angle between the arms and legs be equal to 90 degrees plus beta, where beta is the initial foot angle or rest angle. It can be easily varied by changing the screw points of the corner posts on the bottom plate.
The kinematics of the unit cell is described by 2 scalar parameters for a given direction of the displacement of the central node. The angle alpha, formed by such a direction with the horizontal axis, and the scalar projection u of the displacement vector in this direction. The displaced positions of the elbow and knee joints are easily found at the intersection points of the circle with radius A2, centered at the current position of the central post, and the circles with radius A1, centered at the corner posts. It is safe to assume that the design value of the lateral displacement, hereafter referred to as displacement capacity d, must be sufficiently lower than the minimum value of u, producing a locking configuration of the unit cell. The locking condition is achieved when one or more tendons overlaps the adjacent limbs. It is easily observed that the locking displacement grows appreciably when the rest angle changes from positive to negative, and this is achieved without changing the limb's length and actually slightly reducing the footprint of the device. It is also possible to double the displacement capacity by stacking 2 unit cells one over the other in the vertical direction.
Overall, the displacement capacity depends only on the geometric design variables A1, A2 and beta. Values greater than 90 degrees of the angle between upper and lower arms are needed to build periodic system formed by arrays of unit cells, since the knee elbow joints of adjacent cells do not touch one another if beta is sufficiently greater than 0. This design approach distributes the vertical load P transmitted by the superstructure among multiple central posts, creating a periodic metamaterial.
Let me introduce the bio-inspired character of the seismic isolator. It's worth observing that the shape of the unit cell replicates that of a human body with bent arms and legs. The tendon membrane's capacity to stretch acts as a recentering mechanism of the central post, which regulates the fundamental vibration period of the isolated structure. The extension and release working principle of the membranes produces time fluctuations of kinetic and stored energies, similar to those induced by the stretching and recoil of animals' tendons during running and hopping. Such a response also converts the frequency tuning mechanism associated with the locomotion of animals into a passive mode. While animals move a resonance through the active control of locomotion by muscles, tendons and tissues, the isolator analyzed in this study works in an opposite fashion. It tunes the nonlinear stiffness of the tendons to avoid resonance with the seismic excitation frequencies. It is also possible to actively control the isolator by equipping the device with actuated cables that run on top of the posts or along the tendons, controlled e.g. by actuators embedded in the joints.
Physical models of the SSI were manufactured at the Rapid Prototyping Laboratory of University of Salerno. This was achieved using FDM 3D printers and aluminum confinement plates provided by an online supplier. This examined models features lower arms and legs with a length A1 97 mm, upper arms and legs with length A2 100.5 mm, relative angle between these members equal to 90 degree and overall height of 95 mm including the confinement plates. The tendons were 3D printed using TPU filament for FDM. The sample subjected to the mechanical testing features the central and the corner posts as well as the central and the corner rings fabricated in steel through a parallel lathe available at a partner metal framing company. As anticipated, the slider underneath the central post is a circular disc made of PTFE. Experimental validation tests were designed ad hoc in collaboration with FIP Mech, a leading company in the field of anti-seismic devices based in Padua, Italy. A loading frame equipped with the vertical and horizontal hydraulic actuators was employed to apply unidirectional displacement histories to the bottom plate while subjecting the top plate to a fixed vertical load P. One of the tested prototypes does not have tendons and was analyzed to study the pure friction sliding response of the central post. Prototype 2 features 3D printed TPU tendons. Preconditioning was applied to selected tendons of the prototype.
Let F denote the overall shear force acting on the top plate of the metasolator, base shear of the superstructure. We fitted the mechanical model to the experimental data, accounting for a nonlinear behavior of the friction force at the base of the central post and an hysteretic response of the tendons. The tested samples were subject to sinusoidal cyclic loading with a frequency of 0.40 Hz and D equal to plus minus 50 mm with alpha equal to 0. Three different values of the vertical load were applied to the top plate with P equal to 5, 15 and 25 kN. For the prototype without tendons, the average and effective value of the dynamic friction coefficient μ, which we denote by μ effective, varies between 1.66% with P equal to 5 kN and 1.04% with P equal to 25 kN. The effective fundamental period of vibration, T effective of prototype 2, is equal to 1.32, 2.09 and 2.51 seconds, when P is equal to 5, 15 and 25 kN respectively. The effective damping coefficient of this device ranges between 17 and nearly 28%. These adjustable properties control both the extreme values of the seismic load suffered by the superstructure and the displacement drift between the superstructure and the foundation.
The results of the prototype test can be generalized to metal isolators exhibiting arbitrary values of vertical load capacity P, a displacement capacity D, using the scaling procedure present in the paper. It is possible to reach displacement capacity of 500 mm using a one-layer system with limbs length A approximately 700 mm or a two-layer system with a approximately 350 mm. The design variable T effective and Z effective depend on the geometry of the device, the current value of μ effective, the ratio chi between the design value of the recentering force of the tendons and the maximum vertical load, and a dimensionless parameter lambda that characterize the energy dissipation capacity of the tendon. The friction coefficient can be tuned by playing with the vertical load and the size and material of the slider and the resting plate, while the tendon's energy dissipation properties can be adjusted through their preliminary training, in addition to an optimized design of the geometry and materials. The insertion of special dissipative elements at the midspan of the tendons and the use of recycled materials can also be considered.
We conclude that the biomimetic isolators analyzed in this study help us to forge a novel path to seismic isolation. Such devices with an anthropomorphic character are classified as highly tunable seismic isolators that can be manufactured with customized properties using optimal geometries and sustainable materials easily available around the world. Some key advantages enjoyed by these systems over their current state-of-the-art counterparts are derived from the possibility to tune the displacement capacity acting only on the internal architecture of the unit cell. The uniaxial tension regime of the tendons, up to 40–50% maximum axial strains, which is suitable for a class of materials much larger than the elastomeric products employed in rubber bearings, and the possibility of creating periodic meta-isolators. In addition, the SSI does not require heavy industry and is easily repaired by replacing the tendons after an extreme seismic event.
The level of preliminary training of the tendons can be employed as a peculiar design variable. By adjusting the amplitude of the preconditioning of the tendons, one can suitably design the region of reduced reaction force offered by the device. The design and testing of architectured seismic isolators that feature an independent anti-seismic performance against horizontal and vertical ground motions will be addressed in future work on employing, e.g., linkages that mimic the knee articulation of the human leg in the vertical plane. We wish to warmly thank the co-authors Gianmario Benzoni, formerly University of California, San Diego, and currently University of Salerno, and Graham Milton, University of Utah, for their fundamental contributions to all the phases of the current project. With our great pleasure, this study has been announced in the Research Highlights of Nature of November 24, 2021.